orbiter was launched successfully by NASA in 1988 and was designed to study the Martian atmosphere and provide communications for a variety of other missions already launched to the Red Planet. And all was going well, and the orbiter performed its insertion burn without a problem. And then suddenly, the craft went silent. Future observations found the craft had burnt up in the atmosphere instead of orbiting safely above it. Cause of this error? Well, NASA had sent the communications in imperial units, pounds of force, instead of metric, newtons, that the craft was expecting. And this is why units matter. Letting other people know what a number represents is vital to any measurements. For example, take the number 6. What's it mean? 6 apples, 6 elephants, 6 meters, all vastly different. So adding unit adds context to a measurement. And in this video, I will go through the following. What are SI units? How are SI base units defined? How we use these base units to define all other units? How we can check whether an equation works or not using units. And finally, what are SI prefixes and how do they make writing big or small numbers a lot easier? What are SI units? So SI units are a set of units first introduced by the French in the 1790s. These unified units of measurement into a coherent decimal system called the International System of Units, which is abbreviated to SI in French. These units revolve around a group of 7. These are the second for time, the meter for length, the Kelvin for temperature, the candela for luminous intensity, the kilogram for mass, the mole for amount of substance, and the ampere for current. Now originally, these units would be based on features of the natural world. So for example, these are: the second was based on the rotation of the Earth, the meter on a distance between the equator and the North Pole through Paris, the Kelvin based on water, the candela, I bet you can't guess where this one comes from, yep, a candle, the mole based on the number of atoms in a certain mass of oxygen, and the ampere was based on electrolysis, on the amount of silver that was deposited per second. Now you'll see I've missed the kilogram out, but the kilogram is an interesting one because for starters it's the only one that contains one of our SI prefixes as part of its name, the kilo, more on that later. And B, it's based on an object, it's based on a piece of precision milled and manufactured metal that's held in a safe in Paris. Now the problem with these definitions is measuring all of these things accurately is difficult. And as time goes on and our measurements have been made to higher and higher resolutions, scientists needed a way of making these units defined rather than measured. And as of 2019, all of these units now are defined rather than measured, based on universal constants. SI unit definitions. So, in the lead up to 2019, the people that oversee these units decided that rather than be compared to a certain thing, our units should be based on universal constants and should be clearly defined. So now our units are defined as follows. Now, take care, some real heavy science coming on here, but we'll go slow, we'll get through it, and hopefully I'll simplify each one. So we'll start with the second. So the second is defined by taking a fixed numerical value for a cesium atom. This frequency is called delta V or delta nu, and the frequency we use is the unperturbed, ground state, hyperfine, transition frequency of a cesium-133 atom, and they take it to be 9,192,631,770 hertz, and the hertz is equal to a 1 over a second, or a second to the minus 1. Or to put that in English, because rather than science or geek, this is the frequency of light that a cesium-133 atom absorbs when its atoms are in their lowest possible energy level. Okay, the meter. So the meter is defined by taking the fixed numerical value for the speed of light in a vacuum, which is known as c, to be 299,792,458 meters per second. Or that means that in exactly 1 divided by that number of a second, light travels 1 meter. Okay, the kilogram. The kilogram is defined by taking a fixed value for Planck's constant, h, to be 6.626070015 times 10 to the minus 34 when expressed in units of joule seconds. Now a joule second is equal to a kilogram meters squared per second, when the meter and the second take their previous definitions. Now we'll look at how we get from maybe a joule second to that thing expressed in kilograms meters later on. But you can see this is quite a convoluted definition, and it's probably because kilogram gave scientists the hardest definition here. Okay, the Kelvin. The Kelvin is defined by using Boltzmann's constant, and that is set to be 1.380649 times 10 to the minus 23 when expressed in the units of joules per kilogram, which again is equal to a big long unit, which we will see how we get between these two later on. The candela. Now the candela is a special unit because rather than being defined on something fixed in the universe, this is defined on human perception. And as such, its definition is a bit of a wavy one. And it's defined by taking the fixed numerical value of luminous efficacy of monochromatic radiation of frequency 540 times 10 to the 12 hertz, which they call KCD, to be 683 when expressed in the units of lumens per watt. And a lumen per watt is a candela stereoradian, which is like a 3D angle, per watt. And what that means is basically how we as humans define how bright a light is of a certain frequency. And that frequency actually corresponds to the point that our eyes are most sensitive. The mole is probably the simplest to define, and the mole is exactly 6.02214076 times 10 to the 23 elementary entities, or particles is another way of saying that. And that fixed value is Avogadro's constant. Big N, subscript A. The ampere. The ampere is defined by taking the fixed value now for the elementary charge on an electron to be 1.6022176,634 times 10 to the minus 19 when expressed in the units of coulombs, and a coulomb is equal to an amp second. So these definitions now mean that all measurements are based on the following universal constants: a cesium atom, the speed of light, Planck's constant, Boltzmann's constant, Avogadro's number, and the charge on an electron, which means they should be the same no matter where you are in the universe. Now hopefully people are still watching and you haven't all fallen asleep yet, because that was some heavy science going on. But now we've got our base units, we've got our 7, how do we get to other quantities? Deriving SI units. What is the unit of power? Is every physics teacher's greatest rhetorical question. But what's not a base unit? Neither a joule, a newton, a pascal. Interestingly though, these are all famous scientists' surnames, but none have capital letters. You know you've made it in the world of science when your surname loses its capital letter. Anyway, these are what we call derived units. Derived using equations that are used to calculate the quantities that they represent. Now, you, we, whoever need to be able to represent derived units in their base units. So let's start with the newton. Okay, well, to calculate force, we use Newton's second law, F equals ma. And we can rearrange this to get F equals m v over t, v velocity divided by time, using the definition of what is acceleration. So we look at this, and now our unit for Newton becomes a kilogram times meters per second squared, or kilograms meters per second squared. So what about others? The joule. Well, the joule is energy, and energy is work, and work is force times distance. So a joule is a newton times a meter, or a kilogram meters squared per second squared. Let's go back to the watt. The watt is a joule per second. So it becomes kilograms meters squared per second cubed. And it goes on from there. We can use equations to change units back into their base equivalent. For example, like was done in our definitions. Checking for homogeneity, or does the left equal the right? Now in an A-level exam, you can be asked to check if an equation works. Are the units the same on both sides, or is it homogeneous? Let's look at an example then. So the equation I equals NAVE, or current equals the number of conductors per unit volume times the cross-sectional area times the drift velocity times the charge of an electron. Now this is an equation quite early on in our course you're asked to learn how to derive in Unit 2. And one of the things that we need to do is then check, once we've done our derivation, is our equation right? Does it work? And this is where we do our check for homogeneity. So, current is measured in amps. N is measured in per meter cubed. A, area, is measured in meters squared. V, the velocity, is measured in meters per second. And E is measured in coulombs. So the left hand side of our equation, that's already in base units, that's in amps. The right hand side needs a little help. So if we look at N and we look at A, then we've got per meter cubed and meters squared. So combining these, we just get per meter. Multiply this by meters per second and you get just per second. And so we're left then with coulombs per second. Now, current is the rate of flow of charge by definition, or charge divided by time. Coulombs divided by seconds. So a coulomb per second is just an amp. So now I've got amp on both sides. Our equation is homogeneous. And you can be asked to do others. Not that we're going to do them today, but there are others that you need to be able to do. SI prefixes. So up until now I've talked an awful lot about units, gone through some definitions, some other bits and pieces which, yeah, is a bit boring, I'll admit. Interesting, definitely, but can be a bit boring. But now we need to use them. And we have our base units, so that's alright. Using meters for measuring distances like this long, that's fine. But we need to be able to measure things that range in size from an atom to a galaxy. So to do this, we add prefixes to our units. So, for example, kilo, mega, giga, pico. These all signify powers of 10 in multiples of 3s, or you can think of thousands. Now, generally, if a prefix ends in an A, it is a positive power of 10, and it will be represented with a capital letter. If it's got an O, then it's a negative power of 10 and represented with lowercase letters. Kilo, though, is an odd one out, where it ends in an O and it's a little k, but it's a times 10 to the 3, it's a positive power, and this is because it was one of the first agreed. And it actually comes from the Greek word for thousand, which is kiloi. Now what about our other prefixes? Well, the rest pretty much come from Greek as well, except for milli, which comes from Latin for thousand. So giga means giant, tera means monster, micro means small, nano, dwarf, pico, tiny bit. And once numbers started getting out of this range, to extend the range of our prefixes, they started using names that were a little bit like numbers. So we then have peta, which is from the word for penta, meaning 5. This means times 10 to the 15, or 1,000 times 10 to the 5. Exa comes from hexa, which is times 10 to the 18, or times 10 to the 3, 1,000 to the power of 6. Now, using these prefixes changes the way scientists use standard form. And back on my standard form video, I said I would talk about this in a bit more detail in a future video. So, writing, for example, nanometers is definitely easier than writing times 10 to the minus 9. If not writing it, it's definitely easier to say. So this means that rather than using proper standard form, where remember we only have a single digit in front of the decimal place, scientists use numbers up to 1,000 in front of the decimal place, because any bigger than that and we move to the next prefix. For example, light. The wavelength of green light, written in proper standard form, is 5.5 times 10 to the minus 7 meters. But most physicists will call this 550 nanometers to avoid using standard form, and it actually creeps into everyday life. For example, something like if you're measuring a piece of wood, you might call it 600 millimeters rather than 0.6 meters, or if you want to use standard form, 6 times 10 to the minus 1 meters. So when it comes to science, don't worry about ever using standard form properly. If you just add a prefix to your unit, you can remove the need for it entirely. But most of the time, we, like I said, work in thousands and then put our standard form in if we need to. But the final thing to remember about this is whenever you're doing calculations, unless you're told otherwise, make sure you put the standard form back in and work in the base unit. So not nanometers, make sure you work in meters. Summary. So to sum up this video, units matter. They tell other people what scale you are using to take a measurement. All measurements are based on just 7 units: the second, the meter, the Kelvin, the mole, the ampere, the kilogram and the candela. Although for most of our work we can forget about the candela and just work with the other 6. All of these units are defined based on universal constants. All of our other units we work with are derived using these 7 from the equations that define the quantities. For example, if we want to find force, we use Newton's second law. To reduce the need for standard form, we add prefixes to our units to denote different powers of 10 in multiples of 3. Now, if you want to know more on SI units and how the definitions evolved over time, visit the National Physical Laboratories website. This is where I got a lot of my information from, and I'll put a link in the description. For more on the Mars Climate Orbiter and other imperial to metric conversions going terribly wrong, either listen to 99% Invisible or 99PI's episode Half Measures, or read their article. Again, I'll put a link in the description to this. Now, if you want practice deriving units, converting units, then attempt assignments A2 and A4 from Isaac Physics. Again, a link to these will be below. And well done for making it this far. So thanks for watching, and hopefully you've learned something about the world of measurement from this video.